Value iteration is the first step to understanding reinforcement learning, allowing us to turn model predictions into actionable strategies. Join me today as we learn how to code and think in this new idea space. Welcome. I'm Gregory Talkwine with GNT Learning, and in this episode, we're going to implement value iteration from scratch in an AI gym environment. Now, it's easy enough to find dozens of examples of code online, but where students run into problems is understanding how this scrap of code relates back to the original equation, or for that matter, what this original equation even means. To that end, our goal today is to develop a conceptual understanding that bridges these ideas so that we don't only implement value iteration, but begin to understand the approach to reinforcement problems more generally. To get started, we first need a system that's worth exploring with value iteration. To that end, we're going to use OpenAI Gym to give us an environment to explore, specifically the Frozen Lake environment. Now, AI Gym itself is a popular tool that's used to help wrap these sort of environments in a consistent form so it's easier to do standard reinforcement learning work. Go ahead and import in NumPy and our AI Gym, and we're going to instantiate our environment. Now, AI Gym itself has a lot of built-in environments that are very handy for learning about different facets of machine learning. Today we're going to be using one of the most basic environments available, which is that of the Frozen Lake V0. This Frozen Lake is a simple 4x4 grid of positions where an agent can wander around, maybe fall into the lake, slide around, and try to get to an ultimate goal. To actually visualize this, we can see what this thing looks like a little more clearly. We can use the .render attribute of the environment. Running that, we see that our system is really described by this little figure of characters here. S is the starting position, F is the frozen lake, H is holes that you can fall into, and G is the goal. The goal for this system is to help the agent navigate from the start position to the goal without falling into a hole. What makes this a little more challenging is that there's not a deterministic behavior. When they try to walk across the frozen lakes, they slip and slide and go random directions. So given this system, how do we begin to evaluate what the best strategy or policy is in order to move around? Now, we're going to take a slight diversion here. While it's not necessary for implementing value iteration itself, it is valuable that we understand how this environment works and how the different pieces of reinforcement learning go together. To that end, we're going to spend a moment looking at the AI Gym basics and poking around at this system in a little more detail. We're going to go ahead and make a little marker for that right here. To appreciate what's going on in the environment, let's first imagine our agent starting at the start position S. Okay. To do that, in terms of code, we use env.reset to reinitialize this environment. Next, we need the agent to take an action, A. Now, there's a lot of different actions that can be taken, and our ultimate goal is to have a good set of actions. For now, though, we just want to see how this environment works, so we're going to take advantage of a built-in here called actionSpace.sample. This will allow the agent to take a random valid action from their position. Once they've chosen this action, we can then see what the effect of this action is by asking the environment to execute on this action. Now, the outcome here is going to have several parts. As the result of taking an action, i.e. going left or right or up or down, they're going to end up in a new state. They're going to get some reward. They may or may not be done with the system. And there's going to be a little bit of additional information that we're not going to pay attention to today. And all of these are outcomes from making this action. And the environment that's controlled by AI Gym is updating and keeping track of all these things internally as we step through the system. To see the outcome of what we've done, we can do env.render to again display what the system looks like. And while we're here, we'll take a quick moment to print out what the new state is, what reward we've obtained, if any, and whether or not we're done. So let's go ahead and run this for a single step. What we see here is that the agent chose their action as down, and despite that, they ended up shifting to the right instead. The result of this is that they are in a new state, 1, okay, and here the states are numbered in some fashion. They received a reward of 0, so they didn't fall in a hole, they didn't get to the goal, no reward, and we didn't finish, we're not done. They would finish if they fell in a hole or they reached the goal. So in this way, the agent can repeatedly take actions and wander around until something happens. We want to see what happens as the agent wanders around, in this case randomly. To do that, we don't want to take a single step, but we instead want to just put this little bit of logic into a loop for several steps. For the moment, we're just going to say for a fixed value of 5 steps. Right? They do their little sets of actions, and we're going to go ahead and get rid of the print statement for now. And then we have to do one little check here and say, well, if they're done because they fall in a hole or something like that, we need to go ahead and interrupt the loop. They need to quit trying to take steps. The system will no longer work if you can try to move around after you're done. So by doing this, we can do a little run, and we can see as the agent attempts to wander around for a short period of time. And we can see they move around. In this case, they slide down and eventually go into the hole in the bottom. Our goal is to find the best path available. And there's really two parts to this problem. The first part is, how are you going to understand what's going on in the system? That is, given that you're in a particular location, what is the consequences of all of your actions? Does going right cause me to fall in a hole or not? Do I get a reward for falling in the hole? Do I get penalized for falling in the hole? What actually happens? And the second question is a stepping back one level of saying, once I have those immediate details, how do I craft an overall optimal policy? In value iteration, we assume that we already have perfect knowledge about the first part. We don't need to have the agent run around and collect information and sample the system, build trajectories. Instead, we already have a complete description, and we just need to solve the secondary problem of, once you know how the system works, what is the optimal policy for it? This makes value iteration a little bit simpler case of the more general reinforcement learning, where you have to deal with the interplay between exploration and exploitation of figuring out, do I need to get more information about the system, or do I need to just do better with the information I have? What this means for us in value iteration is that we don't need to actually play this game. We don't need to have the agent walk around. Instead, we're just going to reach into the environment and rip out the specific information about how the system behaves directly. Now that information is stored in env.p. So env.p is a complete description of the statistical nature of the system. Now, at first glance, this looks like a really big data structure with a lot of stuff in it. So let's slow down a little bit and break down how this is actually organized. This env.p contains all the information by state and then by action. So if I put env.p0, it tells me everything about state 0 in the system and what can happen from there. So if you look at that, we see starting from state 0, there's 4 different actions, 0, 1, 2, 3, corresponding to the different cardinal directions. And there is a probabilistic result that can occur because of them. If you just want to look at a specific one, so say now we're going to be the state 0, which is actually the top left, and we're going to take action 0, then there are 3 possible outcomes that can happen. And each of these has a probability of 1/3, and it will put us into a new state, or potentially the same state, state 0, state 0, state 4. It will give us a reward, and then will cause the overall environment to finish the trajectory or episode or not. In this case, none of these options are going to cause us to end. 2 of these actions correspond to bouncing off the wall and not going anywhere. The other one corresponds to moving down. In all cases, there's no reward, and the trajectory continues to run. And in this way, we have access to all of the information about everything that can possibly happen in the system. So if we want to, look at a different state and different action, we can get a richer set of information. In this case, we're starting position 1, where it's possible, if we take action 1, to fall into a hole and be done. So now that we understand what information is available in the system, let's go look at our equation for value iteration and understand how to connect these ideas together. So here is our value iteration section. So this is the overall equation for value iteration. And I know at first glance, especially for those that don't have much of a mathematical background, this can look like an overwhelming set of information. So we're going to take a little bit of time to step through this in a bit of detail. Now here up top, I'm just describing all of the definitions of the various terms, and these are pretty standard values that are used across different reinforcement learning topics and techniques. S is state, A is action, the prime is used to denote if it's the next state or the next action. Now the next 3 are a little more involved. V of S is the value of a particular state. The idea is that this value of a state is the amount of reward I expect to get, i.e. if I am right next to this giant pile of treasure, I feel there's a pretty good chance I'm going to get the reward of that treasure, so my V of S is very high. T is sometimes referred to as P, depending on your source, is the probability of getting into this next state given your current state action pair. So we talked about being on this frozen lake. You try to go one direction, you may slide and go a different direction. So given that you're in a particular place and you try to go a certain direction, what's your probability of ending up in any particular outcome? So there will be multiple different entries in this T for all the different states you might end up in given your state action pair. And then R is just the corresponding reward you get for going on this little journey. Now, this is a piece that people get confused about early on, is you tend to think about rewards as being associated with states, and they're really not. The reward is generally associated with the state, action, and next state trio. The idea here is that you can say, all right, there's a big treasure chest at the end of that hallway, and getting that treasure chest is really great. And that's your next state. So, I want that reward to be the next state. But maybe there's two pathways to get there. One is a nice leisurely stroll, and the other one goes through a wall of fire. Now, in that case, the path you use to get there makes a big difference. If you have to step through that wall of fire to get to that final state, that's not very comfortable. And that could have probably a pretty negative reward overall. And so it's not just the state you're in, but the path you're using to get there in that last step that is part of the reward. So generally speaking, the reward is a combination of both where you are, what you're trying to do, and where you actually end up. All three of those. In the case of the frozen lake, the reward is not for being at the goal. The reward is for getting to the goal. So it's actually taking this last step to the goal that you get rewarded for, not for being at the goal itself. So given these basic terms, let's now talk about the value iteration equation itself. So the value iteration equation is saying the value of any state is simply the result of taking the best possible choice and getting the reward associated with it. So here that's what that max A means. There's many different actions I could take, so the reward I expect to get long term is the one that results from the best possible choice. And then I have to look at the values I get of possible rewards from all those choices. How do I do that? Well, I need to first figure out what happens as a result of my action. So as a result of my action, I end up in some new state S prime, and it's probabilistic in this case because you're sliding across that frozen lake. So we have a probabilistic outcome of next states and then rewards for those next states. And we need to calculate what our expected outcome is. And this is the definition of expectation, is the probability of an event times the value of those individual events. And so by summing over all of the possible next states, we can figure out what our expected return is from taking this action. And the last piece is this detail of what do we mean by reward. And what we really mean is actually both the immediate reward that we get, R, from taking that specific state in that specific action and getting a result, and the future expected rewards that have been discounted according to gamma. But this is the idea that, okay, not only do I get the reward for stepping to that new position that I'm in, I have a reward for, well, now that I'm here, what do I think is going to happen next? But we don't treat all rewards equally. Those future rewards are a little more theoretical. And so we have a discount factor gamma that says those future rewards are not quite as valuable as our current reward. And so we are more encouraged to go after immediate rewards than eventual long-term rewards. This is important for a lot of little reasons in reinforcement learning. Specifically, it's actually going to help with numerical stability on issues like value iteration. But it offers something very physical and normal about a system in that, yeah, you can eventually get that reward probably, but just because it's kind of far off, it really just isn't worth as much as a reward today. So, in totality, what we have here is an equation that gives us the value for every state, assuming the best action, and just measures the possible and expected outcome of the result of taking that action. All right, now let's go ahead and step into the actual code. The first thing we need to do is grab a few little constants for ourselves. So one, we need to know how many states there are in our system. So we'll do env.observation space.n. We'll get the number of actions possible. env.observation, or rather action space. And we also need to set some value of gamma. Now this can be kind of a rich discussion of itself. For the moment, we're just going to say that our gamma is 0.9. Run that. And now we're going to go ahead and start tackling the implementation of this equation into code. We're going to do this from the outside in. All right, so to calculate this, we need to calculate from multiple values of s what this v is. We'll start off by initializing it to a value of 0, and we need a number of these equal to the number of states in the system. All right. Now we need to do this equation for every single one of these values of s, so it's pretty straightforward then. that for every S that we're interested in the range of our number of states, we need to do a calculation. And in that calculation, we're going to need to figure out what's going on this right-hand side. Now, this is a lot of equation here. So we're going to break this into a little bit smaller pieces. We're going to start off by defining Q. Now, Q is just going to be our variable for all the possible results of this summation. And we have to look at multiple ones because we can take the max. So we have to basically do this part of the summation 4 times, once for each of the actions possible. So our Q value here is going to be NP0s of our actions. And then for every one of our actions, we're going to do some work to calculate our value of Q. We'll come back to that in a second. And from there, our value of a particular state S is simply the max of Q. Okay, so let's slow down. We'll see what we've talked about so far here. So we said that we know that the V of S is the result of the max of some summation, right? So this is going to be the summation that we'll figure out the details of in a little bit, right? But we need to take a max over all the possible outcomes. So Q is going to be our vector representing the possible outcomes for our different choices of action A. And then for every action A, we have to update and calculate a value for Q. Now, the choice of variable here, Q, is not random or arbitrary. Q itself is often used to describe these state action pairs. Now, to be careful here, this is not to be confused or say that we're doing anything related to Q-learning. Q-learning also uses the value Q as a more central piece of the calculation, but we're using Q here because that is sort of the standard variable to represent a state action pair combination. And you'll notice that this Q is being initialized inside of the loop for S. So the Q, lowercase q, is existing for each one of the states. So there's really going to be a whole collection of Qs. But as soon as we have the Q and get the result we need for one particular state, we throw it away and just go to the next one. So now we have sort of the outer piece of the structure. How do we actually calculate Q? Well, let's start by thinking about it in terms of the equation as written above. So we already have a loop going through S, and a loop going through A, and really the only piece that's left is this S prime. So if we'd like to have something that looks like for S prime in the range of our number of states, and here note that I'm using S underscore instead of S prime simply because we can't actually use S prime as a variable, so it's much more convenient to just use S underscore. And then we want to do this calculation where we say that Q for a particular action is going to be increased by T of SA S underscore times this equation, pretty much copied almost directly as it's written above. SA S underscore plus gamma of times V of S prime. Or S underscore. Now, the problem here is that's not actually how the data is being given to us, right? We don't actually have a matrix V or a matrix R that contains all the information structured in this way. One could, in principle, build these matrices using the information in the environment variable, env.p. In our case, though, it's going to make more sense to simply loop over env.p and get the values for our calculation. All right. So I'm just going to leave this here actually as a guide and comment this out. This is conceptually what we're trying to do in this next section. What we're actually going to do to implement this is have to make a loop over env.p, and as I said before, it's a combination of state and actions. And then we can, from here, do Q of A plus equals some values. All right. So how do we translate our understanding of the structure of P into something that matches the idea here? Well, the first step is to understand what is being returned here. If we look at a particular combination S and A, let's go back and look at that. What we're getting back is a probability, a next state, a reward, and whether or not we're done. All right. So let's come on down. Let's give those some variable names. Well, probabilities, well, that's what our T values are. The second one was the next state. Okay. The third one was our reward. And the last one is whether or not we're done. Well, since we're not actually walking through the directory, we don't care about whether or not we're done. So we're just going to use underscore here. And that's a really common way to just say, I'm throwing out this piece of information. I don't really care about it. I have to put some variable here because I have to unpack all 4 parts and put them somewhere, but I'm actually not going to use this variable anywhere. So now we have it in terms of a probability, a next state, and a reward. We can see the translation pretty well. So this is simply t times our reward plus gamma times our v of s underscore. So what we've done is we've have the same kind of idea as we did above. We just need to recognize that the translation, instead of having a lookup table where we take s and a and s prime, the lookup is already for the s and the a are already happening for us as part of the p, and what we're left with is only the result of the different s primes that come out of it. So effectively we do have our loop over s prime. From this we can then run the calculation and get our result. Now, since we have this 16 sets of values for the state, it's kind of annoying to look at it directly in just the long vector. So we're going to go ahead and reshape it to 4x4. And this is solely for visualization purposes. And a little typo here. And we run that. And we see what happens after the first iteration of calculating our values. So this, at first glance, might be a little confusing, but this is the correct result. And the way we can see this is that our initial guesses for v's were all 0. And the only time that's going to change is if there's a reward given. And the reward you get in this system is solely for getting to the goal. It's not being in the goal, but getting to the goal. And you can do that by being in this state and going to the right. So this state, if you take a right, there's a 1 in 3 chance you end up at the goal, and so you get a reward. And as such, this has updated the value for what happens here. Now, that value, that information, hasn't propagated to the rest of the system yet. And that's why this is called value iteration. You have to iterate multiple times over the system so that slowly all the different states converge to a solution that's consistent with the values around them. Right now, this value of 0 is consistent with the fact that there's all zeros around it, but this information about there being a reward here hasn't really propagated back to that part of the system. So you have to run this multiple times in a loop. To do that, we're simply going to say for I in range 20, do that, put that over there, and then let this run, for example, for 20 iterations, and we get some updated system or set of values that describe the overall system. And we can see that at first glance this makes some good physical sense, and it's always good to make these little checks. We can see that the state right next to the goal is in fact one that has a high reward. We can also see that the holes in the system, you could go back and look at the math to confirm this for yourself, and the goal itself all have values of 0. So once you fell into the hole, you're not going to get a reward, so of course the value is 0. Now, there is a subtle problem here. This subtle problem is actually not really an issue for value iteration, but it does come up more broadly in reinforcement learning. A lot of times in reinforcement learning, when you have these sort of iterative approaches to problems, and especially when you have that trade-off between exploration and exploitation, you can't rely on the fact that, oh, I can just take the whatever value happens to be my current estimate for the state here and use it to update the value at this position. You're going to get away with it for this case of the value iteration, but it can be a problem more broadly when you get into reinforcement learning. So it's a good idea to just start getting in your head the practice of having distinct iterations where the values of the old estimates and the new estimates are being used and kept separately so that you're always using the previous set of values for your updates. What I mean by this is we need to make a distinction between the value v that we're updating and the value vs underscore that we're using to look up what the previous expectation for that next state is. When you don't take this into account in more complicated systems, you can end up with this positive feedback loop which is numerically unstable. All right. So we're going to go ahead and leave this here as a basic example and begin working on this in a separate piece of a little bit of cleanup. So we're going to go ahead and drop this little bit of descriptive text here. Right? And we're going to create this v old, which is going to be our estimate from the previous step. We do have to give it some initial value at the beginning of our code in order to make sure that everything is going to actually run. because we're going to replace this for loop with a while loop. We'll come back to detail on that in just 1 second. And then what we're going to do is we're going to say that VOLD at the beginning of each iteration is simply going to be a copy of the values once as they were at the end of the previous loop. And then we're going to use this VOLD value for our calculation down here. One side benefit of this VOLD VNew system, besides some numerical stability for more complicated cases, is that it also gives us a better way of knowing what is enough iterations. Here we did 20 above. Is that enough? Do we need to do 5,000? Do we need to do 3? And we can use a while condition to instead pick an exact stopping condition. In this case, we're going to take the absolute value of the difference between the V and the VOLD. And we're going to do this by taking the max in this case and saying, is any of these sites updating by more than some particular threshold? So I'm going to say 1/8 to the -3rd. It's a somewhat arbitrary cutoff. Doing that, we now have values for the different states that are well converged to their final values. And you can see above we used 20 iterations, and that looks like that was about the right answer, although there are some subtle differences. But now we know that we have gone far enough that we can be done with the iterations. So great, we've used value iteration, we've gotten the values. But now we need to go back to what the original question was. The original question is, what is our policy or a plan of action in getting through this maze? We need to know not only what the values were for those best actions, we know what those best actions themselves actually were. Fortunately, we already have the information we need, because when we did this max of Q down here, we took the best value and used that for our estimate. We simply need to keep track of what the best indices of those choices were. So we're going to say policy is going to equal np.zeros for our number of states. And then we're going to say that policy S is np.argmax of Q, where the argmax gives us, instead of the actual value of the max, gives us the position of the max. So it's going to tell us which action was the one that was the best action. And while we're here, let's go ahead and put up a print statement so we can actually see what this policy looks like. And again, we're doing a reshape to 4x4 just to help match how it looks in the original map. All right. And now what we have is our policy laid out in which action 0, 1, 2, or 3 is the best, and the values. Now that's great and all in terms of looking like a result, but how do we actually validate that that's correct? That's not a very human readable format. So we have to do a little bit of extra step if we want to make it sure it's something that we ourselves can interpret, understand, and validate as being correct. So to that end, we need to know what those different actions represent. So after a little poking around and looking at the variables, it's possible to figure out which of the different actions correspond to the different values of action given above. All right. And to make this a little bit more visual, I'm going, instead of using left, right, up, down in terms of words, I'm going to do it in terms of little symbols, so we can make ourselves a nice little map. All right, so we're going to have to compare side by side the map of the system using env.render again, and our own little view of how these things look. So to that end, we're going to do action names. We're going to do list comprehension here, where we're going to convert all of the values from their index 0, 1, 2, 3, that inside of the policy, into these different symbols. Now, a little bit of details here for those not as familiar with list comprehensions. The idea is that basically that we're just doing a loop, and then we're replacing all the values with the result from looking up the I inside of this list of values. Note here that if you were very observant, you would notice there's some decimal points at the end, and that's because when we did the policy initially, we didn't specify that it had to be integers. So these are actually float values, which will fail during lookup, so we have to put an int here to make it into an integer, even though clearly they're integer values 0, 1, 2, 3. And then if we want to visualize this nicely, we need to go ahead and just pack this into a numpy array object so that we can do a nice little reshape 4 on it. Okay. So now we have side by side is a map of the system, and here it has the highlighting from wherever it was left off last in the actual simulation we did above. and our policy map of what the best choice of action is from every single position. Now, this is going to take a moment to think through to make sure this actually makes sense and looks right. And at an immediate glance, it's going to seem like there's some problems here, but this is the correct behavior. If you actually go back and look at the probability distribution for the different actions, what they all amount to is saying, if you want to go in a direction, you try to go right, for example, you have an equal probability of going the direction you want or going orthogonally left or right from that, i.e. if you want to go right, you might go up or down. You never go backwards, though. For example, let's look at this set of states right here. So this position as a whole, so the actual action here is pretty much irrelevant. It's just the result of everything being 0, so it just chose left as the first action. But if you're standing here, the best direction to go is away from the hole, because it's the only way to guarantee you don't fall in. Even though to make progress, you actually do want to go down. To be safe, you have to go left. And the same way, if you look at the state below it, this state, corresponding to this frozen state here, is going to try to go up. Even though it looks like it's going away from the goal, it's the only way to guarantee that by random chance you don't fall into the hole. And so you get some slightly weird looking pathing because of the way the rewards are set up and the probability distribution of your actions. But this is consistent. Right? And you can fiddle through yourself with the logic to some of these. And after a lot of head scratching on sort of the strange behavior that your actions aren't really taking you in directions, they're just guaranteeing they don't take you in the opposite direction, you'll understand that the goal really of your actual actions is always just to make sure you point away from the nearest hole is the optimal strategy. And in this way, we're able to lay out a complete set of actions for our system. Alright, so what did we get done here today? Well, we actually did 3 major things. One, we played around a little bit with just the basics of AIGEM and showed how you could step through a system and look at what's going on. And this is very handy in terms of understanding how an environment works simply by stepping through it. Now, the beauty of value iteration, and this is the second thing we learned, is that we don't actually need to deal with the details of the simulation of sampling the environment. We assume we have the right values because we simply reach into some other database of knowledge to pull out what the distributions look like and then try to solve the equation here, or rather evaluate the equation here, in order to understand what the best possible values and hence policy is for that system. And the last thing we did was we actually went into the details of value iteration, and we showed how you can translate an equation, like the one shown here, into a piece of code. And in this case, the overall answer was that we had to basically have a 3-loop chunk of code that looped over the states, the actions, and the next states to calculate all of the values. The states were because we're trying to calculate the states, the actions because we needed to know which action gave us the best returns, we had to try all of them, and then the next states simply because we needed to look through the possible values of the next state that could be the result of slipping and sliding around in this environment. And in the end, what we have for all of this to show is a relatively small piece of code that does value iteration in a very generic way, and this would really work for any system as long as your number of states and number of actions is correctly defined, and we're then able to visualize in a simplistic way the way in which the policy dictates we should act in order to do the best in the system. Now, if you want to take this further, there's a couple little things. So for one, this system assumed that from every state and that every action was valid. That may not be the case. The way you would handle that is simply in your check here for A and range num actions, you just have an additional if condition that would say, oh, if this action is just not possible in that state, set the value to of Q for that to negative infinity. And then it will simply just never be the max and won't be relevant to the system. Beyond this, going to other methods like policy iteration are really not that much more complicated in terms of the code. It's more a matter of understanding why the assumption of choosing the best action every state gives you this equation as opposed to some other equation, and figuring out how to make the connection between the definitions of those different systems and what you have here. So with that, I encourage you to take this piece of code, try out some other systems, and discover just how far you can get. You'll find, if you get into the more complicated problems, that the limitation becomes this number of states issue. And this is where deep learning and reinforcement learning comes up, is that when you start having billions of potential states, you can't approach it in this sequential fashion of exactly calculating all the results. There's simply more states than maybe you can even store in memory from your machine. So instead, what this value iteration is a really great gateway into thinking about how these reinforcement learning problems are structured. Thanks for watching, and a special thanks to those whose contributions help fund and sustain creating content like this. As always, the code produced today is going to be available on GitHub through a link in the description. Remember to like, subscribe, push all the buttons, click all the things, and I'll see you next time.